Imagine this. You are floating in a spacecraft millions of kilometers from Earth, and directly ahead of you is a hole in reality itself. Not a hole in the ground, not a hole in a wall, but a hole torn into the very fabric of space and time. Light does not bounce off it. Light does not bend around it. Light simply disappears into it and never comes back. And in the next 60 minutes, you are going to fall into it. Not metaphorically, not in theory. We are going to walk through, second by second, exactly what your body, your mind, and the universe around you would experience as you cross the point of no return. Some of what you are about to hear will sound impossible. Some of it will terrify you. And some of it will make you question what time and space actually are. So if you have ever wondered what it truly feels like to die inside a black hole, stay with me, because this is the most extreme journey any object can ever take in the known universe. Before we fall, we need to understand what we are actually falling into, because a black hole is not a hole at all. It is one of the densest, most violent objects that exists anywhere in the cosmos. A black hole forms when a massive star, many times heavier than our sun, runs out of the nuclear fuel that has been holding it up against its own gravity for millions of years. For most of its life, a star is in a constant tug of war. On one side, gravity is trying to crush the star inward. On the other side, the nuclear fusion happening in its core is pushing outward with tremendous energy. As long as the star has fuel to burn, this battle stays balanced. But once the fuel runs out, gravity wins, and it wins catastrophically. The core collapses in on itself in less than a second, and depending on the mass of the star, this collapse can produce a black hole, an object so dense that not even light, the fastest thing in the universe, can escape its pull. To understand why light cannot escape, you have to understand what gravity actually is. Gravity is not simply a force pulling objects together like a rope. According to Einstein's theory of general relativity, gravity is the bending of space and time itself. Every object with mass creates a dent in the fabric of the universe, similar to how a bowling ball placed on a stretched sheet of fabric creates a curve that other smaller objects roll into. The more massive and compact an object is, the deeper that dent becomes. A black hole is so massive and so compressed into such a tiny space that the dent it creates is not just deep, it is infinite. Space folds in on itself so completely that there is no path, no trajectory, no possible direction that leads back out once you cross a certain boundary. That boundary has a name, and it is the most important concept in this entire journey. It is called the event horizon. The event horizon is not a physical surface. There is nothing solid there. You could pass through it without feeling any kind of wall or barrier. It is simply the point of no return, the invisible line in space where the escape velocity needed to break free from the black hole's gravity exceeds the speed of light. Since nothing can travel faster than light, nothing that crosses this line can ever come back out. Not a spacecraft, not a beam of light, not information of any kind. Once you are inside the event horizon, you are not just trapped. You are on a one-way trip toward the center, no matter what you do, no matter how powerful your engines are, no matter which direction you point your ship. Every possible path forward leads deeper in. This is one of the strangest facts in all of physics. Inside a black hole, the future itself points toward the singularity. You cannot choose not to move toward it, the same way you cannot choose not to move forward in time. Now let's actually begin our journey. You are approaching a supermassive black hole, similar in scale to the one at the center of our own galaxy, called Sagittarius A star. This black hole has a mass equivalent to about 4 million suns, compressed into a region smaller than the orbit of Mercury. As you approach from a great distance at first, nothing seems unusual. You do not see a black circle floating in space the way movies often depict it. Instead, what you see is far stranger. Because the black hole's gravity is so intense, it bends the light from stars behind it, wrapping that light around itself like a lens. This creates a glowing ring of distorted starlight surrounding the black hole, known as an Einstein ring. You are essentially looking at the light from stars that are directly behind the black hole, bent around its edges and delivered to your eyes from an angle that should be impossible. It is one of the most visually surreal sights in the entire universe, a shimmering halo of light wrapped around an absolute void. As you continue moving closer, you begin to notice the accretion disk, if this particular black hole has one. This is a swirling ring of superheated gas, dust, and stellar debris that has been captured by the black hole's gravity and is spiraling inward at incredible speeds. As this material falls toward the black hole, it is compressed and heated through friction to temperatures reaching millions of degrees, hot enough to emit intense X-ray radiation. This is actually how astronomers detect black holes in the first place, since the black hole itself emits no light. They detect the blazing hot disk of material orbiting just outside the event horizon. If our journey takes us near an active black hole with a strong accretion disk, this radiation alone would be lethal long before you ever reach the horizon. For the purposes of this simulation, let's imagine you are approaching a quieter, more isolated black hole, one without a violent accretion disk, so that we can focus entirely on the gravitational effects of the fall itself. The first thing you will notice as you get closer is something called gravitational time dilation. Einstein's theory tells us that gravity does not just bend space, it also slows down time. The stronger the gravitational field you are in, the slower time passes for you relative to someone far away in a weaker gravitational field. Near a black hole, this effect becomes extreme. If you had a crew member back on a mothership orbiting safely at a distance, watching you fall through a telescope, they would observe something deeply strange. As you approach the event horizon, your movements would appear to slow down more and more. Your spacecraft's clock, visible to them through their instruments, would appear to tick slower and slower. You would seem to take longer and longer to cover the same distance, even though from your own perspective, you feel like you are moving normally and time feels completely ordinary to you. This difference in perspective is one of the most mind-bending aspects of black hole physics, and it is critically important to understand. Because it means the experience of falling into a black hole is fundamentally different depending on who is watching. From the outside observer's point of view, you would never actually appear to cross the event horizon at all. Instead, your image would appear to freeze at the horizon, growing dimmer and dimmer as the light from your ship gets stretched to longer and longer wavelengths, a phenomenon called gravitational redshift. Eventually, you would fade from view entirely, not because you disappeared, but because the light carrying your image becomes so stretched and faint that it is undetectable. To an outside observer, you become a ghost frozen at the edge of the black hole forever, slowly fading into darkness. But from your own perspective inside the spacecraft, none of this appears to be happening. This is the critical difference. You do not feel yourself slowing down. You do not see your own clock ticking strangely. From where you sit, time feels completely normal and you continue falling, crossing the event horizon in a finite amount of time, based on your own internal clock. This is one of the great paradoxes of black hole physics. Two completely different, equally valid descriptions of the same event. One where you fall in within minutes according to your own experience, and one where an outside observer sees you frozen at the edge for what appears to be an eternity. Both are true. Both are real. This is the nature of relativity, and it shows just how deeply our intuitive understanding of time breaks down near a black hole. Now, as your spacecraft continues its descent, we need to talk about the size of the black hole you are falling into, because this detail changes everything about your fate. If you are falling into a smaller, stellar mass black hole, one formed from the collapse of a single massive star, roughly 10 to 20 times the mass of our Sun, the tidal forces near the event horizon would be so extreme that you would be destroyed long before you ever reached it. This is because of a difference in gravitational pull between the parts of your body closer to the black hole and the parts farther away. Your feet, if you are falling feet first, would be pulled with dramatically more force than your head, because they are slightly closer to the singularity. This difference in pull, called a tidal force, would stretch your body like taffy, thinner and thinner, longer and longer, in a process astrophysicists have nicknamed spaghettification. Your body would be pulled apart at the atomic level, stretched into a thin stream of particles long before you ever cross the horizon of a small black hole. However, our journey today is into a supermassive black hole, and this changes the physics dramatically. Because supermassive black holes have such an enormous radius, the difference in gravitational pull between your head and your feet at the event horizon is actually relatively small. In fact, for a black hole the size of Sagittarius A star, or an even larger one, you could cross the event horizon without being spaghettified immediately. Your body would remain intact, and you would feel essentially normal, still in freefall, still breathing, still alive, as you cross into a region of the universe from which nothing can ever return. This is one of the most unsettling facts about supermassive black holes. Crossing the event horizon might not feel like anything unusual at all. There is no wall, no flash of light, no dramatic boundary. You simply continue falling, and one moment you are in normal space, and the next moment you are inside the black hole, with absolutely no local, immediate sign that anything has changed. This is worth sitting with for a moment, because it defies what most people imagine happens at a black hole's edge. There is no barrier to break through, no resistance, no signal. The event horizon is defined purely by the paths that light can and cannot take, not by any physical structure. This means that if you cross the event horizon of a large enough black hole right now, you would have no way of knowing it happened, at least not immediately. Your instruments might detect subtle changes in the light around you, perhaps an increasing darkness in one direction, as the light from the outside universe becomes concentrated into a shrinking circle above you, an effect caused by the extreme bending of light near the horizon. But there would be no explosion, no jolt, no dramatic moment. Just a quiet, silent crossing into a part of the universe that operates under completely different rules. Once you are inside the event horizon, everything about your reality changes, even if it does not feel that way immediately. Remember what we said earlier, that inside the event horizon, every possible direction leads toward the singularity. This is because space and time essentially swap roles inside a black hole. Outside the event horizon, you can move freely through space, but time always moves forward for you, whether you like it or not. Inside the event horizon, the situation reverses. The singularity is no longer a place you could choose to avoid, the way you could choose not to walk into a wall. Instead, the singularity becomes something more like a moment in time that you cannot avoid, the same way you cannot avoid your own future. Every direction your spacecraft could possibly point, forward, backward, sideways, upward, leads inevitably closer to the singularity. There is no escape maneuver, no burst of engine power, no clever trajectory that changes this outcome. You are not just trapped in space, you are trapped in time itself, hurtling toward an inevitable future. As you continue falling deeper inside the black hole, the tidal forces we discussed earlier begin to intensify dramatically. Even in a supermassive black hole where the pull near the event horizon was gentle, the gravitational gradient becomes steeper and steeper as you approach the singularity. Eventually, no matter how large the black hole is, spaghettification becomes unavoidable. Your body would begin to stretch, first subtly, then dramatically, as the gravitational pull on your feet becomes significantly stronger than the pull on your head. Every cell, every molecule, every atom in your body would be pulled apart along this single axis, stretched into an impossibly thin thread of matter, while simultaneously being compressed from the sides as space itself narrows around you like a funnel. This combination of extreme stretching and extreme compression is one of the most violent processes physics can describe, and it would happen to every single atom of your body simultaneously, all converging on a single point. Let's pause here and talk about what the singularity actually is, because this is where our current understanding of physics reaches its absolute limit. The singularity at the center of a black hole is a place where, according to general relativity, gravity becomes infinite. Space and time curve infinitely, and the density of matter becomes infinite as well. Mathematically, our equations break down completely at this point. They simply stop producing meaningful answers. This does not necessarily mean that a true infinity exists in nature. Most physicists believe that the appearance of infinity in our equations is actually a sign that general relativity is incomplete, and that a deeper theory, one that successfully merges gravity with quantum mechanics, would reveal what is actually happening at the singularity. This missing theory, often called quantum gravity, remains one of the greatest unsolved problems in all of physics. String theory, loop quantum gravity, and several other frameworks attempt to describe what really happens at the singularity, but none of them have been experimentally confirmed. In short, when you ask what actually exists at the center of a black hole, the honest scientific answer is that nobody truly knows. While we do not know what waits at the singularity itself, we do know what would happen to any matter approaching it, based on the physics we understand very well right up until that final mysterious point. As your spacecraft, and eventually your own body, are torn apart by the increasing tidal forces, the individual particles that once made up your ship and your body would continue falling, now as an incredibly thin, hot stream of matter, sometimes called a stream of spaghettified debris. This stream would be compressed to enormous densities and heated by internal friction and gravitational compression to extreme temperatures, likely emitting radiation as it falls the final distance toward the singularity. From the perspective of anyone still watching from a safe distance, though remember, they would never actually see any of this happen in real time. Due to the extreme time dilation, they would only ever see your image frozen and fading at the horizon, the true horror of the final fall hidden from outside observation forever. Now here is where the story gets even stranger, because in the last several decades, physicists have proposed some genuinely mind-bending alternatives to the simple picture of a singularity that we just described. One of the strangest concepts in modern black hole physics is something called the firewall hypothesis. This idea emerged from a deep and unresolved conflict between general relativity and quantum mechanics, known as the black hole information paradox. According to quantum mechanics, information about the physical state of any object, including you and your spacecraft, should never truly be destroyed. It might be scrambled, rearranged, or transformed, but it cannot simply cease to exist. However, according to the classical picture of black holes, anything that falls in eventually reaches the singularity, where it appears to be genuinely destroyed, and its information along with it. This contradiction has puzzled physicists for decades, and one proposed resolution suggests that instead of a smooth crossing at the event horizon, there might actually be a wall of high-energy radiation, a firewall sitting right at the boundary. If this idea is correct, rather than gently floating through the event horizon and only encountering violent tidal forces deep inside, you would instead be instantly incinerated the moment you touched the horizon itself. This remains a hotly debated topic in theoretical physics, with many scientists on different sides of the argument, and it is a perfect example of how much we still do not fully understand about the true nature of black holes. Let's also talk about Hawking radiation, one of the most important discoveries in the history of black hole physics, made by the physicist Stephen Hawking in the 1970s. Hawking demonstrated that black holes are not, in fact, perfectly black. Due to quantum effects occurring right at the event horizon, black holes should very slowly emit a faint stream of radiation over unimaginably long timescales. This happens because of the strange behavior of empty space at the quantum level. Space is never truly empty. It constantly produces pairs of particles and antiparticles that pop into existence and then annihilate each other almost instantly. Near the event horizon of a black hole, however, it is possible for one particle of such a pair to fall into the black hole while the other escapes into space. From the outside, this appears as the black hole slowly emitting radiation, and over time, gradually losing mass and energy. This means that black holes are not eternal. given an unimaginably long period of time, far longer than the current age of the universe. A black hole would theoretically evaporate completely through this process, shrinking smaller and smaller until it vanishes in one final burst of radiation. For the supermassive black hole in our simulation, this process would take far longer than trillions upon trillions of years, so it is not something that would affect your journey in any meaningful way, but it does tell us something profound. Even the most powerful, seemingly eternal objects in the universe are not permanent. Given enough time, even a black hole eventually disappears. Now let's return to your journey and consider one final, fascinating possibility that has captured the imagination of physicists and science fiction writers alike. The idea of a black hole acting as a bridge to another region of space and time, often called an Einstein-Rosen bridge, or more popularly, a wormhole. According to certain solutions of Einstein's equations, particularly those describing a specific theoretical type of black hole called a Kerr black hole, which is a black hole that rotates, it is mathematically possible that the singularity is not a single point, but rather a ring. And in some highly theoretical models, falling through the center of this ring could, in principle, connect to a completely different region of space, or even a different universe entirely, rather than crashing into a singularity. It is critical to understand that this remains purely theoretical and almost certainly does not represent physical reality as most physicists understand it today. Real astrophysical black holes are likely surrounded by such extreme and violent conditions, and such unstable internal structures, that any theoretical wormhole connection would almost certainly collapse and seal itself instantly, long before anything could ever pass through it. Still, it remains one of the most tantalizing possibilities in theoretical physics, the idea that a black hole might not simply be a one-way trip to destruction, but potentially, under very specific and almost certainly unrealistic conditions, a door to somewhere else entirely. Let's take a step back now and talk about what this entire journey teaches us about the universe we live in. Black holes represent the absolute extreme edge of physics as we understand it. They are places where gravity, one of the four fundamental forces that shapes everything from falling apples to orbiting planets to the large-scale structure of the cosmos, becomes so overwhelming that it breaks our conventional understanding of space, time, matter, and even information itself. Studying black holes is not simply an academic exercise. It pushes our greatest scientific minds to develop new theories, new mathematics, and new ways of understanding reality. Every major breakthrough in black hole physics, from Einstein's original equations to Hawking's discovery of black hole radiation, to the direct detection of gravitational waves from colliding black holes in 2015, to the first ever photograph of a black hole's shadow captured by the Event Horizon Telescope in 2019, has expanded human knowledge in ways that were once thought impossible. It is also worth remembering just how common black holes actually are throughout the universe. Far from being rare cosmic oddities, scientists now believe that nearly every large galaxy, including our own Milky Way, contains a supermassive black hole at its very center. Our galaxy's black hole, Sagittarius A star, sits roughly 26,000 light-years away from Earth, meaning we are in no danger from it whatsoever. It has existed quietly at the heart of our galaxy for billions of years, and it will likely continue existing long after our sun has burned out. Beyond supermassive black holes, there are also countless stellar mass black holes scattered throughout every galaxy, remnants of massive stars that have completed their life cycles, along with growing evidence for intermediate mass black holes that sit somewhere between these two categories in size, a missing link that astronomers are still working to fully understand. So what have we truly learned from this journey into the darkest, densest, most extreme objects in the known universe? We have learned that a black hole is not truly a hole at all, but rather a region of space where gravity has become so intense that it fundamentally reshapes the structure of space and time itself. We have learned that the event horizon, the point of no return, is not a physical wall but an invisible boundary defined by the impossibility of escape, even for light. We have learned that falling into a black hole would look and feel completely different depending on whether you are the one falling or the one watching from a safe distance, a profound demonstration of how relative our understanding of time truly is. We have learned that the size of a black hole dramatically changes what would happen to you as you fall in, with smaller black holes destroying you long before you reach the horizon, and larger, supermassive black holes potentially allowing you to cross the horizon while still fully intact, at least for a brief and fleeting moment. And we have learned that at the very center, at the singularity itself, our current laws of physics simply run out of answers, leaving one of the greatest remaining mysteries for future generations of scientists to solve. Perhaps the most humbling lesson of all is this. Despite everything human beings have discovered about the universe, despite landing spacecraft on other worlds, despite photographing galaxies billions of light years away, despite even capturing an image of a black hole's shadow itself, we still do not know, with absolute certainty, what truly happens in that final moment when matter reaches the singularity. It remains one of the last great frontiers of human knowledge, a place where our greatest scientific theories reach their absolute limit, and where imagination and mathematics must work together to try to understand something that may forever remain just beyond our full comprehension. And perhaps that is exactly what makes black holes so endlessly fascinating. They are not simply destructive monsters lurking in the darkness of space. They are the ultimate reminder of how much we still have left to learn about the universe we call home. If this journey to the edge of a black hole expanded the way you think about space, time, and the true scale of the universe, that is exactly what this channel is here to do, week after week, exploring the most extreme, most mysterious, and most awe-inspiring corners of the cosmos. Now let's return to your journey and consider one final, fascinating possibility that has captured the imagination